Imagine a future that's, well, it's not just around the corner, it's actually being built right now. A world where AI agents are basically everywhere.
Hmm.
They're seamlessly handling everything, from your routine customer service chats to incredibly complex stuff like supply chain planning,
Hmm.
autonomously managing logistics, even drafting sophisticated legal documents.
That's amazing, right? Almost sci-fi.
Exactly. But here's the rub, the fundamental challenge, the thing that could really halt this incredible progress.
Yeah.
What if all these powerful, super smart AI agents spoke completely different languages? How do you actually get them to talk to each other, to genuinely collaborate, to move beyond just doing their own isolated tasks and start working together in orchestrated, intelligent ways?
That is the core challenge we're facing today.
Yeah,
And it's way more complex than just a simple translation problem.
right.
Without a common tongue, without established rules of engagement, these individual agents, no matter how smart or powerful they are on their own,
They'll just stay
are
isolated.
little islands.
It's exactly like islands. They won't be able to interact effectively, and that limits their collective potential.
Hmm.
And, by extension, the real transformational power of AI.
That's exactly it. And that's precisely why today we're taking a deep dive into this fascinating, intricate and absolutely crucial world of AI protocol.
So plumbing,
The plumbing. I like that. These aren't just abstract tech specs. They are the new glue, the foundational standards that let all these different artificial intelligence systems finally connect, communicate, and truly collaborate at scale.
Mhm.
Specifically, we're going to unpack 4 key players in this whole standardization game.
Mhm.
The Model Context Protocol, MCP, the A2 Agent Protocol, that's A2A, the Agent Communication Protocol, ACP, and the Agent Network Protocol, ANP.
Quite a few acronyms to get through.
Huh, yeah, definitely.
But our mission in this deep dive is, well, it's ambitious, but it's clear. We really want to demystify these powerful acronyms. We want to break down the fundamental problems they're actually designed to solve.
And explore what their emergence really means for the immediate future of AI development and, importantly, deployment. We'll dig into who's building them, exactly how they work under the hood, and how they are collectively setting the stage for a whole new generation of deeply connected, truly interoperable AI systems.
And to guide us through this pretty complex landscape, we've gathered insights right from the front lines of AI standardization.
The latest stuff.
The very latest. Our sources include recent authoritative announcements from the big players like Google and IBM,
Yeah.
really in-depth research papers like a survey of agent interoperability protocols, and sharp analysis from places like HackerNoon and WorkOS.
Good sources.
Yeah, and all this crucial insight is super recent, published late 2024, early 2025. So we're really looking at the absolute cutting edge here. These are the documents that are actively shaping the future of AI connectivity, like as we speak. So let's kick things off by looking at the big picture, the AI interoperability puzzle. Why is this such a big deal? I mean, it's not just an interesting technical problem, it's a critical bottleneck, right?
Definitely.
Why do we need these sophisticated protocols now? We've seen incredible advancements, haven't we? Individual AI models, smart agents, they're already capable of handling many daily recurring or complex tasks autonomously. That's a quote from the Google developers blog.
Right.
Enterprises everywhere are rapidly building and deploying these specialized agents to scale, automate, and enhance processes, again from Google.
So on the surface, it kind of sounds like AI is already doing everything we could possibly ask.
And it is doing a tremendous amount individually. No question. However, despite that impressive standalone power, most AI agents right now function very much like those islands we mentioned. HackerNoon puts it really well.
Yeah.
They're essentially stuck doing their own thing, operating in isolation and really struggling to talk to each other. This fragmentation, it's not just like an inconvenience, it's a significant systemic bottleneck. It's preventing the next big leap in AI capability.
So the whole is not greater than the sum of its parts right now.
Not even close. The Google developers blog also underlines this, pointing out that enterprises are constantly bumping up against siloed data systems and applications when they try to deploy these agents.
Okay.
Which means all that individual power, it just isn't translating into collective synergistic gains across the organization. The true, profound potential of interconnected AI, it remains largely untapped.
That's such a powerful visual islands of AI. It immediately makes me think of the frustration of trying to build some incredibly complex machine, right? Where every single part comes from a different manufacturer and every single one uses a unique proprietary connector.
Oh yeah, been there.
You might have sourced all the most advanced, powerful pieces from all over the world, but getting them to actually work together as one cohesive unit, it becomes an absolute nightmare. Custom chapters, bespoke integrations, endless debugging.
Total headache. And IBM articulates this perfectly. They note that integrating these multi-agent systems often requires fragile and non-repeatable integrations that are expensive to build.
Fragile, non-repeatable, expensive, not a good combo.
Not at all. You have all the individual components,
Mhm.
but the assembly process itself is the real prohibitive barrier to progress.
Precisely. And this pervasive fragmentation, it seriously limits the true, transformational potential of AI.
Hmm.
When agents can't communicate, they can't effectively multiply productivity gains across an organization. They actually lower overall operational efficiency. And ultimately, they dramatically increase long-term costs because of all those bespoke, fragile integrations that need constant upkeep.
Constant babysitting.
Exactly. So for you, the listener, the learner, this means that while individual AI tools are definitely powerful, these complex multi-agent AI systems, they become inherently harder to build, harder to understand, and way harder to deploy effectively.
Yeah, they certainly don't just plug and play in any meaningful way. Not yet, anyway.
So what does this all mean for the future of AI then? How do we actually bridge these fundamental gaps?
Well, that's where the concept of a universal translator comes in. Yeah. Or maybe more accurately, a kind of shared workspace for AI agents. This isn't just a nice-to-have feature anymore. It's rapidly becoming an absolute necessity if we want AI to move beyond just being specialized tools into becoming truly intelligent collaborative ecosystems.
Right, the next level.
Indeed. These emerging AI protocols are genuinely the missing piece in the AI puzzle, to borrow that phrase from Hacker Noon again.
Yeah.
They're designed to act like a universal translator for artificial intelligence system.
Mhm.
They create standardized languages, common conventions, shared rules of engagement. And this allows AI agents to seamlessly communicate, to genuinely collaborate on complex tasks, and connect effortlessly with third-party tools and data sources. This standardization is the critical key. It's what unlocks the next, much more powerful level of AI capabilities.
Right.
It shifts us from isolated intelligence to networked intelligence.
This push towards standardization is absolutely crucial then, because
Yeah.
without it, developers and enterprises are just constantly battling these challenges, right? Like inconsistent agent interfaces or the never-ending, soul-crushing need for custom connectors for every agent interaction, as IBM puts it so well.
Yeah, the integration tax.
Totally. Think about it in terms of sheer combinatorial explosion.
Right.
If you have N agents that all need to talk to each other, you could potentially need, what is it, NN1, 2 different integration points.
That's one. Exponential growth.
It's an exponential if you have just 10 agents, you need 45 connections. If you have 100, that's almost 5,000 different custom connections.
And it explodes quickly.
No wonder large-scale agent ecosystems become so difficult to maintain and incredibly costly to scale. It's just an unsustainable model for any kind of meaningful growth or widespread adoption.
It truly is unsustainable. And this is why the vision for these AI protocols is so profoundly powerful. Think about how HTTP, the Hypertext Transfer Protocol, totally revolutionized the internet,
Right.
enabled its explosive growth into the interconnected web of information we all rely on today. HTTP allowed any website to talk to any browser, universally.
Yeah, it just worked.
Similarly, these new AI protocols are explicitly setting the stage for a new generation of connected, feature-rich, interoperable AI systems. This future, as the Google developers blog notes with, palpable excitement, promises unprecedented levels of efficiency and innovation just by unleashing collaborative AI on a global scale.
That vision is incredibly compelling. It's not just about making existing AI systems incrementally better. It's about enabling entirely new possibilities, new forms of intelligence, new solutions to problems we previously thought were just too hard. So let's pull back the curtain then. Let's look at these new AI protocols and see precisely how each one contributes to this grand interconnected vision. We should probably start with the Model Context Protocol, MCP.
Sounds like a good place to start. MCP is foundational in many ways.
Okay, let's unpack this then. The Model Context Protocol, MCP, what is it at its heart, and what specific problem is it really trying to solve?
Right, so MCP, it's an open protocol. It was developed by Anthropic, a key player in AI safety and research.
Right, Claude's creators.
Exactly. Its primary focus is to standardize how applications provide context to LLMs and AI applications. The core problem it's tackling, which the Survey of Agent Interoperability Protocols paper highlights really well, is the pervasive lack of context standardization for LLMs.
Okay, lack of context standardization. What does that mean in practice?
Well, imagine an LLM trying to answer your question, but it doesn't know where to look for the relevant information or maybe how to use the tools it might have access to. It's flying blind.
Gotcha.
IBM captures its essence quite succinctly as one model, many tools. It's really about empowering a single, powerful AI model with all the right information consistently at the right time.
One model, many tools. I really like that. It makes a complex idea pretty simple. So this means MCP is all about making sure large language models, the LLMs, get precisely the necessary info, whether that's access to specific tools, relevant data sets, or very precise instructions, but in a standardized way.
Exactly. Standardization is key.
And this is crucial for them to produce not just any output, but outputs that are accurate, relevant, and reliable.
Absolutely.
The goal is to prevent what the survey paper calls ad hoc tool integrations and unreliable behavior. Basically, stop the LLM from making stuff up or hallucinating or just giving irrelevant answers simply because it doesn't have the right data or consistent way to get it. It builds confidence in what the LLM tells you.
That's absolutely right. And HackerNoon offers this brilliant, really relatable analogy for MCP. They call it like USB-C, but for AI.
Huh. Okay, I get that immediately.
Yeah, think about your laptop, right? A single USB-C cable connects it effortlessly to all sorts of peripherals, a monitor, an external drive, power, network. You don't need a different proprietary cable for every single device anymore.
Thank goodness.
Tell me about it. In the same way, MCP aims to make it just as easy for an AI model to connect to your calendar, pull data from your local files, integrate with your CRM, or interact with any API-based tool.
Seamless connection?
That's the goal. The core promise here is no duct taping scripts or middleware, just plug and prompt. It aims to dramatically reduce that integration friction we talked about.
Plug and prompt, that's super intuitive, really speaks to the ease of use it promises. So how does this magic actually happen under the hood? Can you break down its architecture a bit? What are the core components?
Sure. MCP fundamentally relies on a client-server architecture. Pretty standard stuff. You have MCP hosts. These are typically things like AI tools, AI agents themselves, or even IDEs, the integrated development environments programmers use.
Okay.
These act as MCP clients. They initiate connections to MCP servers. Now, these servers act as intelligent bridges. They can connect to either local data, like your files or databases, or remote services, like web APIs.
So the server is the gateway.
Exactly. And each server, importantly, exposes a set of tools it offers through a standardized schema. This schema ensures the client understands exactly what the tool does and how to use it properly. No guesswork.
And what kind of capabilities can these servers offer?
The survey paper outlines 4 core capabilities. First, tools. These are model-controlled interfaces for external APIs, letting the LLM interact with outside services. Second, resources. This is application-controlled data, think audio, video, text files, providing the LLM with relevant context it needs. Third, prompts. These are user-controlled templates used to guide the LLM's behavior and responses. And fourth, sampling. These are mechanisms for managing the output generation process, allowing control over things like randomness or determinism in the response.
Got it. Tools, resources, prompts, sampling. And how do these clients and servers actually talk to each other? What's the technical language they use?
For message exchange, MCP primarily uses JSON RPC 2.0.
Yeah.
Both HackerNoon and the survey paper point this out.
JSON RPC. Okay.
Yeah, it's a lightweight remote procedure call protocol. Think of it as just a standardized way for the client to ask the server to do something specific, like, hey, fetch my calendar events, and get a clear, structured response back.
Makes sense.
This communication typically runs over HTTP, the standard web protocol, and it includes optional server-sent events, or SSE, for network communication.
SSE, why is that useful?
SSE is particularly good for real-time updates. It allows the server to push information to the client whenever something new happens, without the client needing to constantly ask, anything new, anything new.
Yeah.
It makes the interaction more dynamic and responsive.
JSON RPC over HTTP with optional SSE for real time seems pretty robust. Is there a defined process, like a life cycle, for how these connections are set up, managed, and eventually shut down?
Yes, absolutely. MCP defines a structured 3-phase life cycle. This ensures reliability and proper resource management, which is critical.
Okay, what are the phases?
The first phase is initialization. This is where the client and server agree on the specific protocol version they'll use and exchange their capabilities, basically, telling each other what tools or resources they can offer or might need. It's like a handshake.
Right.
Next is operation. This is the main phase where the actual JSON RPC calls happen back and forth. Timeouts are carefully managed here too. If a response doesn't come back quickly enough, the client can cancel or retry.
Important for reliability.
Very. And finally, there's shutdown. This ensures a clean termination of the connection. Both sides are responsible for releasing any resources they were holding and gracefully closing connections. This prevents things like lingering processes or data inconsistencies.
Okay, so we're talking about LLMs directly accessing everything from my local calendar and emails to schedule meetings, fetching project docs, even getting real-time web data through a scraping server. That sounds incredibly powerful for creating these context-aware agents. Can you give us a few more practical examples? How might this look day to day?
Absolutely. A really common application is an LLM agent accessing local calendars and emails to schedule meetings. It could intelligently find open slots for everyone involved, send out the invitations, all based on real-time availability pulled via MCP.
Nice. That would save a lot of hassle.
Totally. Another example, fetching project-specific documentation and libraries for context-aware code suggestions directly from your company's internal knowledge base or version control system. Imagine how much easier that makes a developer's life.
Yeah, huge productivity boost.
And Hacker Noon also highlights the ability to pass real-time, fresh, accurate data retrieved via a web-scraping MCP server to your AI agent. Think about an AI assistant that can instantly get you the absolute latest market data, stock prices, or breaking news headlines that are directly relevant to your query, bypassing potentially stale, cached information.
Giving an AI agent direct access to so much potentially sensitive data, especially stuff stored locally, that immediately brings up a critical question. Security. What are the key security considerations for MCP given these capabilities?
Security is absolutely paramount, and it's considered throughout the entire MCP lifecycle. During the creation phase, for example, threats include things like installer spoofing, meaning malicious actors could trick users into installing compromised MCP clients or servers, and also supply chain backdoors, where vulnerabilities get introduced sneakily during the software development process itself.
Nasty. How do you fight that?
Mitigations include enforcing software bill of materials, or SBOMs, basically a detailed list of all software components along with rigorous digital signatures to verify the software's authenticity and integrity. Checking the label, essentially.
Okay. What about during the operation phase, when it's actually running?
During operation, critical risks include tool poisoning, where malicious prompts could trick the LLM into misusing its tools for harmful purposes.
Yeah. Prompt injection attacks.
Exactly. Also, credential theft, compromising access tokens, and command injection, where harmful commands get inserted into the interaction flow.
So how are those handled?
These are addressed through strict schema validation of all inputs, implementing robust OAuth 2.1 for secure authorization, using crucial techniques like sandboxing, which isolates the agent's execution environment to limit potential damage, and rigorous input sanitization to block harmful data before it even reaches the LLM.
And updates. Are there risks there too?
Yes. During the update phases, risks like version drift, where different parts of the system end up running incompatible versions, and unsigned tool manifests could introduce vulnerabilities. These require strong controls like GitOps, using version control for infrastructure configuration, for automated drift detection, and strict signature checks on all tool manifests before they're deployed.
That's a pretty comprehensive view of the security considerations. Now, IBM made an interesting point, really important distinction regarding MCP. They stated it falls short for multi-agent systems. Can you elaborate on that? It sounds like it's really designed to empower one LLM with tools, not necessarily for multiple agents to talk to each other.
That's a crucial point that really clarifies MCP's scope. While MCP is incredibly powerful for single models interacting with their tools, IBM rightly highlights its limitations when it comes to true, complex, multi-agent systems.
What are those limitations specifically?
Well, they include a lack of finer-grained delta streaming. This means MCP isn't really optimized for sending continuous, small, incremental updates of information back and forth, which is often needed in dynamic agent-to-agent conversations. It also doesn't inherently support memory sharing across servers, which is often essential for collaborative workflows where multiple agents need a shared understanding of the context or the state of a task.
Okay, so no shared memory, not great for real-time updates between agents. Anything else?
Furthermore, IBM argues that MCP's reliance on JSON RPC can introduce a certain level of complexity compared to simpler, arguably more flexible REST-based designs, which are often preferred for broader multi-agent integration across different systems.
Gotcha. So different technical approaches.
Fundamentally, yes. IBM emphasizes that MCP is primarily about giving a person better tools by enhancing a single AI model's capabilities. In contrast, true multi-agent systems are more about enabling people to form teams by allowing agents to collaborate effectively as peers.
That makes perfect sense. So MCP empowers the individual agent, gives it its toolkit, makes it smarter on its own. But if we want multiple agents to actually work together seamlessly to form those teams IBM mentioned, how do we do that?
Well, that directly brings us to Google's Agent-to-Agent protocol, or A2A, that's designed specifically for that collaborative aspect.
All right, so we've established MCP empowers individual AI models, gives them their tools and context. Now let's shift gears from empowering single agents to getting multiple agents to truly collaborate, especially within, say, an organizational context. That's where Google's agent protocol A2A steps in.
Exactly. A2A is designed to tackle that multi-agent collaboration challenge head-on.
So what exactly is A2A, and what's its core purpose, especially considering the limitations of MCP we just discussed?
Right. A2A is a significant new open protocol that Google launched, I believe, is April 9th, 2025. And this wasn't just Google working in isolation. It was a massive collaborative effort. They had contributions from over 50 technology partners.
50 partners. Wow. Who was involved?
Big names. Think Atlassian, Box, Cohere, Salesforce, and many others. It shows broad industry interest. Its core mission is really impactful to allow AI agents to communicate with each other, securely exchange information, and coordinate actions. And crucially, regardless of whether they were built by different vendors or in a different framework.
Okay, that vendor and framework agnostic part sounds like a huge deal for enterprises, breaking down those silos.
It's absolutely critical for maximizing the real-world benefits of agentic AI within a complex enterprise environment. A2A enables agents to collaborate in a dynamic, multi-agent ecosystem across siloed data systems and applications.
So it connects the islands?
Precisely. Think about a large company, different departments using different software, different databases, different AI models, maybe from different vendors. A2A provides that connective tissue, that common language, allowing agents built in one system to interact smoothly with agents in another. The promise here is big, to drive unprecedented levels of efficiency and innovation by fundamentally breaking down those internal barriers that traditionally silo data and processes.
Right. Unlocking that systemic value.
Exactly. It's about unlocking a new layer of productivity and problem solving across the entire organization, not just within one team or tool.
Hacker Noon had another great analogy for A2A that I really liked. They described it as like Slack for AI agents.
Ah, that's pretty good.
Yeah, a shared workspace where bots can chat, assign tasks, and get things done. Makes it immediately relatable. Now, what's the relationship between A2A and MCP, the protocol we just discussed? Are they competitors or do they work together?
Definitely not competing. They're explicitly designed to be complementary. Google themselves state that A2A complements Anthropic's Model Context Protocol, MCP, and that A2A can build on top of MCP.
Okay, so they work together.
Yes, they work even better together. The distinction is quite clear. MCP focuses on giving a single LLM the tools and context it needs to do its job. A2A, on the other hand, focuses on how multiple agents, which might individually be using MCP internally to get their own capabilities, communicate and coordinate their actions with each other.
Ah, okay. So an agent might use MCP to talk to its tools.
Right.
And then use A2A to talk to another agent to collaborate on a bigger task.
You've got it. That's exactly the idea.
That really clarifies how they fit together. So how does A2A actually work then? What are its underlying design principles that enable this kind of enterprise collaboration?
A2A facilitates communication in a sort of peer-like way between a client agent, which formulates the tasks, and a remote agent, which acts on those tasks. It starts with a user, and this could be a human operator or even another sophisticated agent who initiates a request.
Okay.
The client agent then intelligently discovers and invokes suitable remote agents to help fulfill that request. It's designed around 5 core principles to ensure it's effective and scalable for enterprise use.
What are those principles?
First, embrace agentic capabilities. This means it supports true multi-agent scenarios where agents don't necessarily share memory, but can still cooperate by exchanging structured messages. Second, build on existing standards. Big one for adoption. It leverages widely accepted web standards like HTTP, server-sent events, SSE for real-time updates, and JSON RPC for structured communication. Makes integration easier.
Makes sense. Keep it familiar.
Third, secure by default. Absolutely paramount for enterprise use. A2A is engineered with enterprise-grade authentication, authorization, and data encryption baked in from the ground up. Fourth, support for long-running tasks. Many real business processes aren't instant. A2A provides mechanisms for real-time feedback, notifications, status updates for tasks that might take hours or even days.
Right. Crucial for practical workflows.
And fifth, modality agnostic. It's not just text. A2A supports various communication modes, including efficient audio and video streaming, allowing for much richer interactions between agents or with users.
That's a really robust set of principles, clearly aimed at real-world enterprise needs. Can you elaborate a bit more on the core components? Like, how do agents actually find each other's capabilities?
Certainly. Some key capabilities within A2A include capability discovery. Agents advertise their skills using something called an agent card.
Agent card, what's that?
It's basically a standardized JSON format document. It describes what the agent does, its inputs, outputs, any constraints. This allows a client agent to dynamically find and select the most appropriate remote agent for a specific job, like reading an agent's business card.
Okay, makes sense.
What else? Then there's task management. A2A defines a clear task object with a defined lifecycle states like pending, running, completed, failed. This provides a structured way to define a unit of work, and the outputs are consistently called artifacts. Standardizes the workflow.
Task and artifacts. Got it.
There's also collaboration. Agents send messages to each other for context, provide updates, request info, or offer user instructions. It's flexible enough for complex, multi-turn conversations. And finally, user experience negotiation. A2A can handle different content types like images, video, or even interactive iframes. Agents can adapt their communication based on what the user's interface can handle. Send a chart instead of raw data, for example.
That sounds like a highly structured yet pretty flexible way for agents to interact. Can you give us a concrete, real-world example of A2A in action? Put it in an enterprise context.
Yeah, Google provides a perfect example, streamlining the candidate sourcing process for a hiring manager. This is something many companies struggle with.
Oh, yeah, definitely.
Instead of the manager manually juggling multiple systems, HR software, LinkedIn, email, calendars, their personal AI agent, acting as the A2A client, can interact with other specialized agents across the organization.
Okay, how?
For instance, it could ping a sourcing agent to identify potential candidates from various internal and external databases, then pass those leads to a screening agent that uses AI to review applications against the job requirements.
Automating the first pass.
Exactly. Next, a scheduling agent could arrange interviews by coordinating with everyone's calendars via their respective agents. And maybe even another specialized agent kicks off background checks. All these specialized agents seamlessly collaborate across systems to source a qualified job candidate, with the hiring manager's agent acting as the smart orchestrator, providing a unified, automated experience.
That truly illustrates the power of collaboration across different systems, different departments using different tools. But with all this interaction, all this sensitive data flying around HR data, candidate info, especially within an enterprise where security is everything.
What are the key security considerations for A2A?
Security is absolutely baked into A2A's design, considering its entire life cycle. During creation, threats include things like agent card and manifest spoofing, where bad actors could tamper with an agent's advertised capabilities or identity.
How is that stopped?
Mitigation involves requiring digitally signed agent cards and strict checks and verification when an agent registers itself, verifying authenticity.
Okay, and during operation,
Yeah.
when tasks are running. During operation, critical risks include task injection and command forgery. This is where malicious actors might try to manipulate the JSON RPC calls to make agents do unauthorized things, and also push notification hijacking, intercepting, or spoofing critical updates.
Right. How are those tackled?
These are addressed by enforcing TLS for encrypted transport, that's standard HTTPS encryption, using JSON web signatures, or JWS, to cryptographically sign message parts, ensuring they haven't been tampered with, and issuing scoped capability tokens.
Scope tokens.
Yeah, these tokens grant only the minimum necessary permissions for a specific task, and often for a limited time. Limits the blast radius if something goes wrong. Principle of least privilege.
Got it. What about updates and termination?
For updates, risks include unauthorized capability injection, sneaking in new unvetted functions, and version drift running incompatible software versions. These are mitigated using immutable version manifests. Once an agent version's capabilities are defined, they can't be easily tampered with. And using GitOps for robust version control and drift detection helps keep everything aligned. Finally, in termination, you need to avoid orphaned resources, lingering connections, or data. This is handled by implementing explicit shutdown hooks in the agents and centralizing audit logging for full traceability and resource cleanup.
It's clear A2A is a powerful tool, really designed for that robust, secure, enterprise-level agent collaboration. But what about something more broadly applicable? Maybe an open source standard for agent-to-agent communication that doesn't necessarily target just one specific ecosystem or a large corporation's internal network.
That's the perfect setup for our next protocol, the Agent Communication Protocol, or ACP. It aims for that broader, more open standard.
So we've covered MCP for single models getting their tools and A2A for robust enterprise collaboration. Now let's explore the Agent Communication Protocol, ACP. What is it fundamentally, and what makes it unique, especially compared to something like A2A?
Right, ACP. Its position is a truly open standard. It was developed initially by IBM Research's BAI initiative, but importantly, it's now stewarded under the Linux Foundation.
Linux Foundation. That signals serious open governance.
Exactly. That open governance is a key differentiator. Its main goal is to enable interoperability between different AI agents, regardless of their underlying frameworks, technologies, or developers. IBM is very explicit about its focus. Many agents securely working as peers, no vendor lock-in, open governance.
Okay, no vendor lock-in, open governance. That sounds like a direct contrast to A2A's approach, which you said was optimized for Google's ecosystem, even if it's technically open.
It's definitely a different philosophy. While A2A involves many partners, its core development and direction are heavily influenced by Google. ACP, under the Linux Foundation, aims for a more neutral ground, trying to be the universal standard for everyone without favoring any single vendor. It's about universal, neutral interoperability from the ground up.
So ACP really emphasizes those open standards and vendor neutrality, makes it potentially accessible to a much wider range of developers, startups, academics, maybe?
That's the idea. IBM notes that ACP represents a fundamental shift from a fragmented, ad hoc ecosystem to an interconnected network of agents, where each agent can discover, understand, and collaborate with others. It's designed to transform those siloed agents into interoperable agentic systems with easier integration and collaboration.
That sounds incredibly ambitious, foundational, really.
It absolutely is. Hacker Noon evocatively calls ACP a delivery service for AI agents, implying, reliable, structured communication.
Right.
It also floats that provocative idea we discussed earlier. Could ACP become a potential HTTP for AI agents? That truly universal layer.
The ultimate goal.
And IBM contrasts it directly with MCP again, stating that while MCP is about giving a person better tools by empowering one LLM, ACP is about enabling people to form teams, allowing agents to work collaboratively within AI applications. It's focused on collective action, not just making one agent smarter.
That distinction really helps clarify their different roles. IBM also mentioned that ACP is seen as the next step following the Model Context Protocol, MCP. How does it build on or differ from MCP technically?
Yeah, ACP definitely moves beyond just connecting a single LLM to its tools, which is MCP's sweet spot. ACP defines how agents operate and communicate with each other as peers, enabling complex, multi-turn interactions and collaborations.
And technically, you mentioned REST earlier.
Right. IBM specifically points out that ACP's REST-based design is generally considered more lightweight and integration-friendly than MCP's JSON RPC, especially for broad adoption across diverse systems.
Why is REST seen as more integration-friendly here?
Well, RESTful APIs are incredibly widespread and well understood across the web development world. Millions of developers already know how to work with them. This makes it potentially easier for diverse systems to integrate ACP without needing complex client libraries or specialized knowledge. The design choice aims for simpler, more universal integration into existing production environments.
Interesting. So how does ACP actually work? Can you walk us through its architecture and key features, especially how agents find and talk to each other in this model?
Sure. ACP defines a streamlined three-role architecture to manage agent interactions effectively. First, you have an agent client. This is the entity that kicks off the communication and needs to discover available agents.
Okay, the initiator.
Then there's the ACP server. This acts as a central protocol broker. It maintains an agent registry, think of it as a directory or yellow pages of available agents and their capabilities. The ACP server also enforces policies to ensure secure and compliant interactions.
The traffic cop and directory.
Kind of, yeah. And finally, the ACP agent. This is the actual execution endpoint, where the agent's specific domain logic lives. This is the brain that actually performs the requested work.
Client, server, agent. Got it. What are the core concepts that define how these agents present themselves and exchange information within ACP?
Central to ACP is the agent detail. This is a JSON or YAML document, human-readable formats, serving as an agent's public identity and capability profile. It's used for discovery. Think of it as the agent's resume or public profile, listing its skills and how to interact with it.
The agent's profile page.
Pretty much. Then you have discovery mechanisms. These allow clients to dynamically locate agents. This can happen through centralized registries managed by an ACP server or through decentralized manifest files, often hosted at a standard web location like well-known-agent.aml. This allows for flexible deployment models, centralized or decentralized.
Okay, flexibility and discovery. How about the actual work requests?
The task request is the structured unit of work. It's composed of ordered message parts. These parts can include textual inputs, like natural language instructions, or binary payloads, such as images, documents, or other data files. All communication uses a message structure with explicit MME content type annotations.
MIME types, like in email attachments.
Exactly like that. It means every part of a message is clearly labeled with its type, text plain, application JSON, image caping, whatever it is. This ensures the receiving agent knows exactly how to interpret each part correctly, crucial for handling diverse data types. And finally, the results of the agent's work are consistently represented as artifacts. These could be structured JSON, plain text, or binary files containing the outcome.
Task requests with typed parts results as artifacts. Seems clear. You mentioned the REST-based communication style earlier. What does that mean in practice, and why is it a standout feature?
ACP leverages REST-based communication using standard HTTP conventions. Think GET, POST, PUT, delete methods, acting on resources defined by URLs. As IBM highlights, this makes it easy to integrate into production for countless developers already familiar with building and consuming web APIs. That's a massive advantage over more specialized or complex protocols.
Familiarity breeds adoption.
Exactly. It supports synchronous, asynchronous, and streaming interactions. So agents can have real-time back-and-forth chats, send requests, and get responses later, like submitting a long job, or stream continuous data feeds. It also supports multimodal messages, text, images, JSON, all within the same structured conversation, allowing for really rich, expressive exchanges between agents.
And the no SDK required part, that sounds significant.
It really is. A truly notable feature, emphasized by IBM, is that basic interaction doesn't require any specialized libraries. You don't need a specific ACP software development kit to talk to an ACP agent. This means you could potentially interact with ACP agents using widely available command line tools like curl or graphical tools like Postman, things many developers use daily. It drastically lowers the barrier to entry for experimenting and integrating. Of course, an SDK is available for convenience and more complex use cases, but it's not strictly necessary to get started.
No SDK required for basic interaction is a massive deal for broad adoption. Really underlines that open source vendor neutral philosophy. What about offline discovery? That sounds quite unique for an agent protocol. How does that work?
It is quite innovative. A key feature of ACP is offline discovery. ACP agents can embed their metadata, their agent detail profile, directly into their distribution package, like inside a container image or a deployment archive. So this means an agent's capabilities and identity can be discovered by analyzing its package even when it's not actively running or connected to a central registry. This is incredibly useful for supporting scale-to-zero environments.
Scale-to-zero?
Yeah, where computational resources, like cloud functions or containers, are dynamically allocated only when an agent is needed and then spun down completely when idle to save costs. Offline discovery means you can still know what agents are available in your environment, even if they're currently asleep. It's a very pragmatic design choice for building large, flexible, and cost-efficient agent ecosystems where not every single agent needs to be persistently online 24/7.
That makes a lot of sense for efficiency. So stepping back, why exactly do we need ACP when we have other protocols emerging like A2A? What specific pressing challenges is it designed to solve in the real world?
ACP directly tackles several critical challenges that are hindering broader AI adoption right now. First, framework diversity. As we know, hundreds, maybe thousands of agents are being built using wildly different frameworks. LangChain, AutoGen, CrewAI, countless custom solutions. ACP provides the universal interoperable language that transcends these specific framework boundaries.
The Tower of Babel problem for AI frameworks.
Exactly. Second, custom integration. It aims to eliminate the costly, time-consuming, and often brittle need to write bespoke one-off connectors for every single agent interaction. Third, it directly tackles the exponential development problem, that N12 integration nightmare we keep mentioning. It aims to simplify that dramatically by standardizing the interface. And finally, it handles cross-organization considerations. This is a big one. It facilitates secure and efficient integration across different companies or departments, each potentially having its own security models, data formats, and IT policies. It's really about making inter-organizational AI collaboration frictionless and scalable.
That manufacturing company example from IBM really seemed to illustrate how ACP solves those cross-organizational challenges. Could you walk us through that specific scenario again? It felt very tangible.
Certainly. Imagine a manufacturing company's autonomous agent that manages its production schedules. This agent needs real-time shipping estimates from a logistics provider's agent to optimize when things are made and shipped.
Okay, common need.
Without ACP, this seemingly simple exchange requires a complex, bespoke integration between their two separate systems. This means engineers from both companies have to manually negotiate data formats, build custom API calls, handle authentication securely between organizations, manage service availability. It's expensive, brittle, and notoriously difficult to scale if you want to add more logistics partners later.
Right, a whole new project for each partner.
Exactly. With ACP, the solution becomes much more elegant. Each company simply wraps its existing agent, the scheduling agent and the shipping estimate agent, with a standardized ACP interface. The manufacturing agent sends an ACP-compliant task request with the order details to the logistics agent. The logistics agent processes it and responds with the real-time shipping options as structured artifacts.
Same outcome, much less hassle.
Precisely. Both systems achieve agentic collaboration without exposing their internal proprietary logic or writing custom integrations. And crucially, new logistics partners can be onboarded simply by implementing the ACP standard on their end. It makes the entire supply chain ecosystem much more dynamic, scalable, and streamlined.
That really highlights the power of open standardization for unlocking new business models and efficiencies. What about security for ACP, especially given its open nature and aspirations for peer-to-peer interaction across organizations?
Security is absolutely critical for ACP, precisely because of its aim for broad, open interoperability. During creation, there's a risk of metadata spoofing and supply chain attacks. Forged agent detail manifests could impersonate legitimate agents or sneak vulnerabilities into the ecosystem.
How's that mitigated?
Mitigations include requiring digital signing of manifests to verify their origin and integrity, and enforcing strong CI/CD signature checks in the development pipeline before deployment, basically verifying the agent's identity papers.
Okay, during operation.
During operation, critical risks include message tampering and MITM, man-in-the-middle attacks, where communications are intercepted or altered in transit, and auth-flaws and unauthorized access, allowing bad actors to interact with agents they shouldn't.
Standard web security concerns, but for agents.
Exactly. These are tackled by using TLS for encrypted transport, HTTPS, cryptographically signing individual message parts with JSON web signatures, JWS, to ensure integrity even within the encrypted channel, and applying capability-scoped, short-lived tokens for authentication, again, limiting permissions and exposure time.
And updates and termination, similar to A2A.
Similar risks, similar approaches. During update, version rollback and config drift pose risks. These are addressed using immutable version manifests once published, a version can't be changed, and leveraging GitOps for systematic drift detection and management. Finally, in termination, you need to prevent orphaned resources and audit gaps. This means ensuring all access tokens are properly revoked and centralizing audit logging for comprehensive traceability of all interactions.
We've now seen MCP empowering single LLMs and A2A and ACP enabling agents to work together in more structured, often enterprise or cross-organizational environments. But what about agents collaborating across the vast, truly open internet, securely, decentrally, without any single company or registry necessarily in charge?
Now you're talking about the final frontier, in a way.
Yeah.
That brings us directly to the Agent Network Protocol, ANP, designed for exactly that challenge. The open internet.
So we've explored protocols for single models, for enterprise collaboration, for open peer-to-peer interaction. Now let's zoom out to the biggest playing field, the open internet itself. This is where the Agent Network Protocol, ANP, comes in, aiming for global, decentralized agent interaction. What exactly is ANP, and what's its core purpose in this grand vision?
ANP is described as a decentralized peer-to-peer communication standard designed for cross-platform agent interoperability on the open internet. Its primary goal is to facilitate internet-based agent collaboration on a truly massive scale.
Decentralized, peer-to-peer, open internet. That sounds fundamentally different.
It is. The core insight driving ANP is that while the modern internet is incredibly effective and optimized for human interaction, it's often suboptimal for autonomous agents.
Why suboptimal?
Because agents, especially operating across untrusted networks, need things humans don't necessarily prioritize in the same way. Low latency, API-native communication, and decentralized identity validation to function reliably and securely. ANP steps in to provide that critical missing foundation for truly global machine-to-machine interactions at scale. It aims to enable agents to operate with the same kind of ease and trust that humans experience on the web today, but in a way that's built for machines first.
Suboptimal for autonomous agents. That's a really concise and insightful way to put it. Highlights the need for a new paradigm. How does HackerNoon describe ANP? Do they have an analogy for this one too?
They do. HackerNoon refers to ANP as a sophisticated postal service for AI agents.
Okay, like ACP was a delivery service. This is the postal service. More infrastructure.
Kind of. It highlights that instead of just sending simple messages or letters, agents using ANP can have real-time conversations or subscribe to specific information channels, like getting registered mail or subscribing to a magazine. It implies a highly dynamic, asynchronous, and reliable system for transmitting complex messages between autonomous entities anywhere on the globe. It's about ensuring every message gets to the right digital mailbox, securely and efficiently, no matter where the agent is hosted.
That analogy helps paint the picture of its broad scope. Now let's get into the details. How does ANP actually work? What are its core architectural components that enable this decentralized internet-scale collaboration?
ANP is built upon a layered protocol architecture, using HTTP as its foundational transport layer, just like the web we know. But its core components are specifically designed for a decentralized, trust-minimized environment.
Okay, what's key component number one?
Agent identity. This is absolutely crucial in an open, untrusted network. ANP uses decentralized identifiers, or DDoDs. These are part of the W3C DID specification, a global standard.
DDs. Heard of those in the blockchain context sometimes.
Right. They provide a globally unique, cryptographically verifiable identity that doesn't rely on a single centralized authority like a domain registrar or a certificate authority. ANP specifically leverages the did.WPA method, which means web-based DDoDs.
Did.WPA. What's special about that?
It's key because it means agents can prove their identity and find the associated public keys using standard HTTPS web infrastructure by hosting a DI document at a specific URL tied to their identifier. It leverages the existing web for identity resolution, making it practical. This creates a secure, self-sovereign identity for each agent, allowing them to trust who they're talking to on the open internet based on cryptography, not just a company name.
Self-sovereign identity for agents. Interesting. What's next?
Agent Description Protocol, ADP. These are JSON-LD formatted documents. JSON-LD is JSON for linking data, making it machine-readable and semantically rich. These ADP documents contain structured metadata about the agent, its name, its specific capabilities, the communication protocols it supports, like maybe it also speaks ACP or A2A, its authentication schemes, and its service endpoints, where to actually connect.
Yeah.
This is the agent's public, machine-readable profile, allowing other agents to understand what it offers and how to interact.
So JSON-D for identity, ADP for capabilities. How do agents find these ADPs?
Through the Discovery Directory. To enable scalable discovery across the vast internet, agents expose their presence, specifically their ADP, at a standardized well-known agent descriptions endpoint on their host server. This is similar to how websites used well-known for things like security policies.
Ah, the .well-known convention.
Exactly. This allows for scalable agent indexing and search by external services. Think dedicated agent search engines or directories that can crawl the internet looking for these well-known endpoints. Indexing available agents, much like Google crawls and indexes websites for human consumption today.
So it's like building the infrastructure for a public Yellow Pages or a search engine specifically for AI agents on the internet.
Okay, so they found each other using DDDs and ADPs. How do they actually talk?
ANP accommodates diverse communication interfaces. It supports structured interfaces like JSON or PC or maybe formal open API definitions for precise programmatic interactions where the message format and sequence are strictly defined. Predictable machine-to-machine talk.
Got it.
But it also allows for natural language interfaces, where communication might be handled via YAML or similar human-readable formats, enabling more flexible, potentially even conversational interactions, although likely still structured under the hood.
And you mentioned negotiation. Yes, this is really advanced. The Meta Protocol Negotiator. This component allows agents to dynamically align protocols. Imagine two agents meet, and they don't initially share a common communication protocol beyond basic ANP. They can exchange natural language descriptions of their communication requirements to negotiate and instantiate a compatible interaction protocol on the fly.
Wow, agents literally negotiating how they're going to talk to each other.
That's the concept. It ensures maximum interoperability even with a huge degree of diversity across agent implementations worldwide.
That's incredibly advanced. What about the full life cycle of an ANP agent in this open, decentralized world, from creation to retirement?
The ANP agent lifecycle follows those canonical phases we've seen. Creation involves generating the agent's D2D and publishing its ADP document. Operation is when agents authenticate using cryptographic credentials derived from their DD documents and interact via their chosen interfaces. Update allows for revisions to the ADP, maybe adding new capabilities or changing endpoints, with these changes hopefully propagating automatically via those indexing services. And finally, termination involves properly deactivating the agent's identity, removing its DID and ADP from public directories, and revoking any active access tokens for a clean and secure shutdown.
And what's the underlying transport and data format used for ANP messages generally?
ANP primarily relies on HTTPS for transport, leveraging the universality of the web. For data formatting, as mentioned, it uses JSON LD, JSON for linking data. This RDF-based format is powerful because it allows for semantic clarity using established vocabularies, often from schema.org. This means that data exchanged has clear, machine-understandable meaning across different agents, even if they come from totally different domains or developers. That semantic clarity is crucial for achieving true, meaningful interoperability on the open internet.
This really sounds like the ultimate vision for global AI agent collaboration, almost like creating a parallel AI native internet running on top of our existing one. What are the primary use cases ANP is designed to unlock?
Exactly. ANP provides the foundation for scalable, cross-platform agent marketplaces and AI-native web interaction. Imagine a global marketplace where diverse AI agents offer specialized services, financial analysis, scientific computation, creative content generation, logistics optimization, you name it.
A global app store, but for AI agent capabilities.
Kinda, yeah. ANP allows these agents to be discovered, evaluated for trustworthiness via their DDs, and seamlessly integrated by other agents or applications from anywhere on the internet. This could foster entirely new, complex, dynamic AI ecosystems that can self-assemble on demand to solve problems that are too big or complex for any single agent or organization today.
Can you give us a tangible example of ANP in action, something that helps bring this AI native web concept to life?
Certainly. Consider a specialized weather forecasting agent run by a meteorological institute. It could publish alerts, severe storm warnings, heat advisories, etc. via the ANP. Then, various smart home agents, regardless of their manufacturer, Google Home, Alexa, Apple HomeKit custom ones, underlying technology or geographic location, could subscribe to receive them based on their location or user preferences. So an irrigation system agent could receive a heavy rain incoming alert and automatically postpone watering for the day. A smart window agent could receive a high wind warning and close itself autonomously. ANP ensures these critical messages are delivered quickly, securely, and to the right recipient, enabling truly decentralized real-time information exchange and autonomous coordination between systems owned by completely different entities across the open internet without needing a central broker for every interaction.
With an open internet environment like that, where agents are interacting across potentially untrusted networks, security concerns must be at their absolute peak. What are the key security considerations specifically for ANP?
Security for ANP is indeed paramount, arguably the most critical aspect due to its decentralized open internet nature. Key threats include identity spoofing of DID documents during creation or operation, malicious actors trying to impersonate legitimate agents. Also, unverified agents potentially bypassing crucial DD checks during interaction. Another major concern is interface tampering, altering the structured interfaces advertised in the ADP, or injecting malicious inputs into natural language endpoints to manipulate an agent's behavior.
Right, manipulating the agent's inputs or understanding.
Exactly. During updates, stale descriptions with outdated metadata are a risk. An agent might interact with a service whose capabilities or security posture have changed unknowingly. And post-termination orphaned identifiers could persist, potentially leading to identity reuse vulnerabilities if not handled carefully.
Those are serious threats for a global network. What are the robust mitigations ANP proposes to address these high-stakes security challenges?
The mitigations have to be comprehensive. To prevent identity spoofing, ANP enforces HTTPS-hosted DIDs, rigorous DNS verification methods, and strong DID signature validation. This ensures an agent's identity is cryptographically verifiable and tied to a legitimate, controllable web presence. For ongoing operations, authentication happens via the public keys listed in the DID document. Agents verify each other's digital identities through cryptography. Furthermore, cryptographic signing of interfaces, like the ADP itself, helps ensure that the advertised capabilities and interaction methods haven't been tampered with since publication.
Okay, strong crypto for identity and integrity. What about stale data?
To combat stale data, the idea relies on automated crawling of agent descriptions by those indexing services to ensure they have the most up-to-date metadata. Using expiration timestamps for DIDs also ensures proper deactivation and helps prevent orphaned identities from being exploited later. These measures collectively aim to build a framework of decentralized trust, which is absolutely essential for a functioning open agent network.
Okay, wow. Now that we've unpacked each of these fascinating, powerful protocols, MCP, A2A, ACP, and ANP, let's try to connect the dots. Let's see how they fit into the bigger picture of AI's future. It's clear that each serve a distinct purpose, but how do they all work together? Or do they?
That's the million-dollar question, right? How does this all fit together?
We've navigated through the intricate details of MCP, A2A, ACP, and ANP. What's the big takeaway message about how these protocols relate to each other? Are they actually in competition, all vying to be the single standard, or is it more harmonious?
It's absolutely vital to understand that these protocols aren't necessarily competitors. That's a really crucial insight. Instead, they address different layers of the AI system integration stack and often complement one another, as IBM points out really clearly.
Different layers, okay.
Yeah, the consensus from that comprehensive survey paper we keep referencing is crystal clear. No single protocol suffices across all contexts. It just doesn't work that way. This is because the problem of AI interoperability isn't monolithic. It operates on various levels, from how one model accesses its tools, to how teams collaborate internally, to how organizations connect, all the way out to global decentralized networks.
So each protocol serves a distinct yet interconnected purpose, targeting different tiers of interoperability.
Precisely. It's not a winner-take-all scenario at all. It's much more like a symphony of specialized instruments, right? Each playing its essential part to create a complex, harmonious whole.
I like that symphony analogy. Can you elaborate on how each protocol plays its distinct part within this layered ecosystem? Recap their roles quickly.
Sure. MCP, remember, focuses on enriching a single LLM's context. It standardizes how it connects to external tools and data, making that individual AI more capable and reliable. Its focus is narrow but deep.
Okay, the individual musician's sheet music and instrument.
Kind of. The A2A is designed for enterprise-scale task delegation and orchestration. It allows agents within trusted organizational boundaries to collaborate securely and efficiently on complex, multi-step workflows. Think internal team coordination.
Right, the internal sections plan.
ACP offers a more general, vendor-neutral, agent-to-agent communication framework, typically using that lightweight, RESTful interface. This makes it ideal for broad cross-framework and cross-organization peer-to-peer interactions where neutrality is key.
The standard interface for different sections to talk.
Exactly. And finally, ANP takes it to the broadest level. It extends interoperability to decentralized open internet agent marketplaces, focusing on secure, identity-verified interactions across untrusted public networks using DADs.
The global broadcast and coordination mechanism.
You got it. Each solves a specific type of interoperability challenge, layering on top of or alongside the others.
Okay, let's revisit our house building analogy to really nail this down. MCP is like the highly specialized tools for one craftsperson. That high-tech laser level or specialized framing nail gun empowers the individual.
Perfect. Building on that, ACP and A2A are like different blueprints or communication plans for how the entire construction crew collaborates on site. A2A, with its enterprise focus, might be the internal team's highly structured playbook, maybe from a big construction firm, optimized for their specific tools and internal processes, highly efficient within their walls.
Right.
ACP, being more open and vendor neutral, is like the universal building code and standard communication protocols. It allows multiple different specialist companies, the plumbers, the electricians, the roofers, to bring their teams and equipment to the same job site and understand exactly how to work together safely and effectively, even if they use totally different internal project management systems.
Okay, that makes sense. And ANP then, where does that fit in the construction world?
ANP, in this analogy, is much bigger. It's the Global Supply Chain Directory, the International Building Standards Organization, the internet infrastructure itself that allows different construction companies from anywhere in the world to find each other, advertise their unique specialized services, like, say, historical restoration experts, exchange resources securely, and even contract specialized teams from far away. It provides the foundational discovery, who offers what, and secure communication needed for a truly global construction market, enabling massive, complex projects that draw on expertise and resources from anywhere, way beyond a single job site or even a single large company.
That's a fantastic way to visualize it all fitting together. So what does this layered complementary approach mean for our listener, the learner? Why does understanding this interconnectedness really matter to them?
It matters because this layered approach means AI systems can be built with increasing sophistication and reach scaling from internal tools all the way up to global agent networks without getting locked into a single vendor's ecosystem or a single limiting framework.
Freedom and flexibility.
Exactly. For you, the listener, it means more flexible, more powerful, and far more adaptable AI solutions are coming. You won't necessarily be restricted to one company's vision. You can potentially mix and match the best tools and agents for any given problem, fostering unprecedented innovation and choice in how AI is built, deployed, and leveraged. It's about enabling a truly composable AI future, building complex systems from interoperable parts.
To really solidify this, let's do a quick comparative overview. Can you highlight some of the key distinguishing features across all four protocols, pulling from that survey paper's comparison table?
Absolutely. The Survey Papers Table 7 provides a great side-by-side look. For instance, their architecture model varies significantly, as we've discussed. MCP is that tight client-server model. ACP uses a brokered client-server with an agent registry acting as middleman. A2A operates more like a peer-to-peer interaction between a client and a remote agent. And ANP is designed as that fully decentralized peer-to-peer network.
And how they handle agent discovery, that seems fundamental for collaboration.
Right? Discovery mechanisms range quite a bit. From simpler manual or static URL lookup for MCP, moving to registry-based discovery for ACP, using its agent registry, then more advanced search engine-like discovery for A2A within enterprise contexts, and finally that fully decentralized discovery using well-known endpoints and indexing services for ANP across the open internet.
What about identity and authentication? How do they prove who's who?
That also differs significantly. You see, token-based authentication often relying on existing enterprise identity systems in MCP and A2A. But then you move to strong decentralized identifier DID-based authentication in ACP and especially ANP. In ANP particularly, trust is established cryptographically using those DID.WBA web-based DIDs, crucially without needing a central authority.
Okay, and their message format and target scope. These seem like core differentiators in what they're trying to achieve.
Absolutely. MCP primarily uses JSON RPC 2.0. That structured remote procedure call format. ACP opts for structured multi-part messages with those explicit MIN types, enabling rich multimodal communication text, images, JSON payloads, all in one exchange. A2A focuses on its specific task plus artifact messaging pattern over JSON, really optimized for those structured enterprise workflows. And ANP leverages JSON LD, JSON for linking data, with semantic web principles like schema.org vocabularies. This allows for a highly expressive open web format, ensuring the meaning of the data is preserved across diverse agents, which is critical for the open internet.
And their target scopes, just to recap.
MCP targets LLM external tool integration, making one model smarter. ACP is designed for model-agnostic, infrastructure-level agents communicating as peers, often across organizations. A2A focuses on trusted enterprise task delegation and orchestration, primarily within an organization's boundaries. And ANP is explicitly designed for open internet agent interconnectivity and fostering those large-scale agent marketplaces.
The IBM source highlighted a key philosophical difference between A2A and ACP, even though they both aim for agent-to-agent communication. Can you elaborate on that again and maybe touch on their respective strengths and limitations?
Yes, this is a really crucial distinction to grasp. While A2A and ACP both facilitate agent-to-agent communication, A2A, coming from Google, is admittedly optimized for Google's ecosystem. Its strength lies in potentially deep integration with Google Cloud Services and robust enterprise-grade security features designed for known, trusted environments. Its perceived limitation might be less emphasis on true vendor agnosticism outside that Google-centric world.
Okay, and ACP.
ACP, being driven by IBM and the Linux Foundation, explicitly focuses on being vendor neutral, with open governance and broad ecosystem alignment. Its strength is its lightweight REST-based design, which encourages broad adoption and actively tries to reduce vendor lock-in, making it incredibly flexible. Its potential limitation could be that ensuring security and policy enforcement might require more explicit configuration at the ACP server level compared to the more implicitly trusted walled garden environment A2A often assumes.
What about MCP and ANP's core strengths and limitations in this comparison?
For MCP, its core strength is providing that precise, context-aware tool invocation for single LLMs, making them highly effective individually. Its limitation, as IBM noted, is its relative complexity, JSON RPC, for broad multi-agent scenarios, and its lack of features like delta streaming or inherent shared memory needed for complex collaborative tasks.
And ANP?
For ANP, its major strength is enabling truly decentralized, cross-platform agent marketplaces on the open internet, secured by strong DID-based identity verification, fostering unprecedented scale and innovation. Its limitation is the inherent overhead and complexity that comes with dynamic meta-protocol negotiation and managing trust effectively in an entirely decentralized, untrusted environment. It requires very robust cryptographic measures and careful design to work reliably at scale.
Given this complementary nature, then, where each protocol really has its own niche and strengths, how might organizations practically adopt these? Is there a recommended roadmap for integrating them into an evolving AI strategy? Seems like you wouldn't just jump straight to ANP, for example.
Absolutely not. And the survey paper thoughtfully proposes exactly that, a practical multi-stage deployment strategy for agent interoperability. This isn't about picking one winner, it's a phased approach. It's designed to guide organizations to gradually adopt the most suitable agent communication standards as their AI needs mature and evolve. It helps manage complexity while maximizing interoperability benefits along the way. It's really a blueprint for building the future of interconnected AI in a systematic, manageable fashion.
That sounds like a really pragmatic way forward. Tell us about these stages. Where does an organization typically begin on this interoperability journey?
The initial phase, Stage 1 MCP for tool invocation, is really the foundational step. It focuses squarely on establishing secure, structured interaction between an organization's core LLMs and their essential external tools, internal databases, external APIs, specific business functions using MCP's client-server model.
So just making the core LLMs more capable first.
Exactly. This is where an organization ensures its large language models can reliably access and utilize the context and capabilities they need. It's about empowering those individual LLMs, making them immediately more useful and less prone to making things up because they lack context. Think of it as making your individual AI assistants incredibly competent and reliable first. Get the basics right.
Okay, so once those foundational tool connections are solid, what's the next logical step on this roadmap? How do you move towards collaboration?
Once individual LLMs are reliably empowered with their tools, Stage 2 layers on ACP for rich interaction. ACP is introduced here to enable asynchronous, multimodal, and REST-native messaging between different agents or components.
Moving from model to tool to agent.
Precisely. This supports richer agent conversations and allows for easier integration with broader RESTful ecosystems that exist within most companies, going beyond just simple tool invocation. It moves the needle from a single LLM using tools towards basic, flexible communication and collaboration between agents, even if they're built using different frameworks. This stage is crucial for starting to break down those internal silos between different AI projects or teams.
And for more complex internal collaborations, perhaps those highly structured workflows that need tight orchestration within a company, like that hiring example.
That's exactly where Stage 3 A2A for enterprise collaboration comes into play. For those more sophisticated enterprise environments with complex, multi-step, multi-agent workflows, A2A enables robust multi-agent workflows and task orchestration. It leverages those structured capability cards for precise discovery and focuses heavily on secure inter-organizational collaboration in trusted contexts.
So A2A is for the heavy-duty internal teamwork.
Generally, yes. This stage is ideal for managing critical end-to-end business processes, like our hiring manager example, where multiple specialized agents need to coordinate tightly and securely within the company's network boundaries. It provides the necessary structure, task management, and security posture for large-scale internal agent teams working together.
And finally, that grand vision for open internet collaboration, the truly decentralized future. Where does that fit?
That's Stage 4 ANP for Open Agent Markets. This is the final phase described in the roadmap. It extends interoperability capabilities out to the truly open internet using ANP. It provides the decentralized agent discovery, DID-based identity verification, and peer-to-peer communication needed for building and participating in scalable, cross-platform agent marketplaces. This is where agents can find and securely interact with services globally across organizational boundaries.
So it's a progression.
Exactly. This phased approach allows organizations to progress logically, from internal, tightly controlled LLM tool integrations, MCP, to flexible inter-agent communication, ACP, to structured internal collaboration, A2A, and finally, potentially reaching out to broad, decentralized open internet agent networks, ANP. It allows them to maximize interoperability benefits while carefully managing complexity and security risks at each step. It truly is a comprehensive blueprint for building towards the future of interconnected AI.
Wow, what a truly deep dive into the foundational technologies that are literally shaping the next era of artificial intelligence. We've really journeyed through the Model Context Protocol, the Agent-to-Agent Protocol, the Agent Communication Protocol, and the Agent Network Protocol.
It covered a lot of ground.
We really did. And we've seen how these protocols are not just dry technical specifications buried in documentation. They are the fundamental building blocks. They're addressing the critical, urgent challenge of AI agent interoperability head on.
They really are the missing pieces, the essential plumbing, that will truly unleash the collaborative power of AI. And understanding these frameworks, it's no longer just for specialized engineers deep in the weeds. It's becoming essential for anyone, business leaders, product managers, developers, students, anyone looking to navigate and thrive in this rapidly evolving landscape of agentic AI.
Absolutely. It's about recognizing the underlying infrastructure that's going to power the next generation of intelligent systems. So for you, the listener, this means being better equipped to understand and strategically leverage AI's immense potential, to innovate faster, to scale your operations more effectively, and frankly, to maintain a critical competitive advantage in this incredibly fast-changing technological environment. Hacker Noon put that really well.
Yeah, it's about knowing not just what AI agents can do individually, but how they'll actually communicate and coordinate to do things even better together, creating unprecedented value and tackling complex problems through that emergent collective intelligence.
So here's where it gets really interesting. If these protocols, or some evolution of them, truly become the HTTP for AI agents, paving the way for this seamless global machine-to-machine communication, what completely new forms of collaboration and innovation will emerge when AI agents can truly and seamlessly work together across any boundary, organizational, geographical, technical, just like humans communicate and collaborate sometimes on the internet today.
It opens up incredible possibilities. What previously unsolvable problems, things we haven't even conceived of yet, might AI agents tackle together in the very near future once these standards become universally adopted and refined? Think about global challenges, climate change modeling, personalized medicine at scale, truly optimizing global supply chains.
The possibilities, when you think about that level of automated, intelligent collaboration, they really do feel limitless. It's a fundamental shift.
It really is. And we definitely encourage you, the listener, to delve deeper into these fascinating developments if this has sparked your interest. You can explore the full specification drafts. A2A specs are usually on Google's developer site. ACP details are often on the BAI site or linked from the Linux Foundation. And you can often find projects like ANP being developed transparently on platforms like GitHub.
The future of AI interoperability is literally being built right now. Code is being written, standards are being debated, and hopefully you now feel exceptionally well-informed about the foundational pieces that are going to make it all happen.
Hopefully so. It's a complex but incredibly important area to understand.
Thank you so much for joining us on the Steam Dive.
My pleasure.